So for this example, we have bituminous coal with this will given multiple analysis. Um, and then we want to find the high value. So in this case, it's like if this is on a dry basis or a bookshelf basis or ash basis, so we will take this as the same basis. But to find the value, we have the formula for that. So 3K 30 times the ultimate analysis of and that of carbon was 0.75. And then for the secondary, we have 144 to 12. For hydrogen, it's 0.75 minus oxygen is 0.07 overheat. And it plus 9 for weight. And so for it, 0.06. If you solve this, you get this x to 30 or 70.71 kilojoules per gram. Okay. So for the next example, we have this fuel oil is given with this measurement heating of 20 ppi, and then you have 15.6 degrees Celsius. So you want to find and determine, so you want to find that HFP of this fuel oil is in the following and also in the kilojoule per liters. So for the estimate formula, so you have a THP for estimate, but so it was 80 here. You have one, and this is 130 plus 139.6 to the API. So since we don't know yet the API, which is what we want to find first, so actually this is a base given. So this one we just multiplied by 20. So the final answer should be 43.9 kilojoule per bit. Now for the identity value using the standards formula, you have 51705 minus, what is that? You have 8790. So we want to now find that specific gravity. So since we have the API as given, then we can solve for the specific gravity. Okay. So we can find the specific gravity at 3.6 degrees Celsius. To find that the SG at 15.6 Celsius, that will be, it's not explicit. So the API is equal to 141.5 over SG at 15.6 and then minus 131.5. So SG here is 80 pound. So calculator, that should be 0.9339. Okay. So therefore, you can find the high rating value going back to this again. So the high rating value can be found to be 44 0.37 per data. Okay. For letter T, specifically, yeah, that. That's the, so that page. So for the dynamic value in kilojoule per liter, so it is not explicitly said, then we have to answer here. So probably we want to find book estimate and use a bit of status formula. So basically, if you want to find the heating value in terms of kilojoule per liter, you just multiply the density. So we know that water is, so the density of water, at the strike of here, is 100 kilogram per cubic meter. But if you multiply this by 1,000 liter per cubic meter, sorry, it should be 1 cubic meter per 1,000 liter. Then it cancel out this negative, so it will be 1 kilogram per liter. And we know that specific gravity is just of any fluid, right? Is just the density of the fluid over the density of water. Okay? So therefore, you can find the density of the fluid you will see the density of water times the specific gravity of. Okay, so we already know that this is the specific gravity. So we just multiply 0.9339 by the density of water, which is 1 kilogram per liter. So basically, it's just 0.9339 kilogram per liter. So we can just multiply this one. We can multiply this density to find that. So, therefore, the high heating value in terms of liters for ASME is 40.922 kilojoule per kilogram multiplied by 0.9339 a kilogram per liter. No? So we will get this formula 0.19 kilojoule per liter. And then for the pure stainless formula, we just get this one. It's a little one. So 44,037 kilojoule per kilogram multiplied by the same that's kilogram per liter. So the answer should be, but we can double check this. So this is kilojoule per liter. Okay. I think we're the box way. So we should box this. So this. And for letter C, I want to find the lower rating value. So for the lower rating value, that is the high rating value. Minus 9, sorry, not 9. This is 2442. And then the mass of the water vapor. So to find the mass of water vapor, that is 9H plus M plus air fuel ratio times the specific humidity of air. So we can cancel this out since the studies recently said that we have moist air and you don't have inherent moisture in the liquid. So we just have this. Now to find each here, since we don't have an ultimate analysis, so we can find each as I think this is um, 26 minus 15. This is minus 15, and then your specific gravity. Now, take note that this is in percentage, though. So we have to divide this later. We have to divide, sorry, percent. We have to divide this by 100 to make this endless mutations. No. So the lower rating value is high rating value. I will just solve one, the ASME version. So we have 922 minus 2442. And then I can just substitute this 9 each. So we have 9 H, right? So H here is 26 minus 15 times the specific gravity. Specific gravity is 0.9339. And then that's it. And you divide this by 100 because it is a percent. So to convert this to decimal places, we have to divide by 100. The low rating value can be found to be also 4187 kilojoule per liter. Okay. And then for the last one, so we want to determine the high rating value at 50 Celsius, 8 kilojoule per liter. So trivia actually is that the high rating value will stay the same at whatever temperature actually. So the high rating value, so I think here, high rating value is constant at whatever temperature. But any given temperature, as long as the unit is in kilojoule per kilogram. But again, so the high rating value of your fuel will remain constant as long as it is in kilojoule per kilogram. But we know that the specific gravity will change depending on the temperature. Therefore, if the unit is in kilojoule per liter, it will be different because of the change in density. Okay, let's see that. So we want to find the density at 16 degrees Celsius. Uh, so, to find the specific gravity at 60 degrees Celsius, that will be the specific gravity at 50.6 multiplied by 1 minus um, 0.007. Okay, that's 37, right? Okay, and then you have the temperature. So the temperature here, and then 50.6. So this is the correction factor for the specific gravity at the temperatures. So let's change this to 0.9339, and then you change this into the temperature, which is 60. So you can find the specific gravity at 60 degrees Celsius to be about 905. So therefore, the density at 60 degrees Celsius of this fluid is 0.905 kilogram per liter. So in other words, we just multiply 1 kilogram per liter of water here. So we can find diuretic value for both ASME and Europe standards to be 49, 32 kilojoule per kilogram multiplied by 0.905 kilogram per liter, which is this, so 39.4 kilojoule per liter. For the Europe standards version, this will be 14 to 80. Just I will check. 037. So 44037. And then kilojoule per kilogram multiplied by the density of 0.905 kilogram per liter. So this will be it should be it's an equal step. So 39 or 7 kilojoule per liter. So okay, so that's it. Let's keep that. It's the next.